Okay, hello everyone. Welcome to this webinar on inquiry-based learning, so science inquiry-based learning. We've got Bob Kibble with us today. He's got a lot of experience in teaching secondary and university level. He's written loads of books about science for primary and secondary kids as well. And he's the editor-in-chief of our Max Science series, which I'm sure some of you will know. We're really lucky to have him with us today. We really hope that you enjoy this session with him. We'd love to hear from you as we go along. So you can just let us know that you're hearing us, ask any questions, let us know where you're from. We love to see all of that information and get to know you a little bit. So without much further ado, Bob, over to you.
Thank you very much, Elliot, and hello everyone. I would like to say good morning because it's the morning where I am here in Scotland, but I guess that where you are, it's another time of the day. But nevertheless, thank you for joining in. We have about 45-50 minutes of presentation followed by questions, and I won't be able to take questions as we go through, but I hope that we'll have time towards the end to address one or two questions. I'll do my best to leave some time. I'm going to control the slides from here, and I'm going to show you first of all a place that I know very well because this is my hometown in Scotland. And if you ever go to Scotland, I hope you'll pass through Peebles and enjoy its beauty. And it's just like this morning. If you want to know where we are, it's on a map. It's south of Edinburgh, about 30 miles, about 45 kilometres south of Edinburgh. And it's in a place called the Scottish Borders, which is full of rivers for fishing and has a famous tweed industry of long ago. Now very much a tourist town. So that's where I'm speaking from. Not actually in the parkland, but I'm at home. And I hope that one day, if I don't get to see you all in person, which I hope I do, that maybe one or two of you will have a chance to visit Scotland if you haven't yet visited this lovely country. So let's talk about today's menu. And I've loosely broken things down to these areas of interest. So I'll try and cover something of each of these. And in so doing, I'll stop off on a few key ideas en route, which will be these ideas. And I'll say something about them all, because they're all part and parcel of the whole process of inquiry. So that's really our menu for the day, for this session. We'll start off by having a look at these images. There's something in common, of course, that they all have. That's the reason I've shown you them, is that they're all showing scientists at work, but they're all showing scientists at work in groups. They're showing science as a social experience, and modern teaching has recognised that children need to work collaboratively together, and that really plays into our hands when we're teaching inquiry skills, because inquiry is a community activity. And the black and white photograph at the bottom left shows fairly modern day scientists. I would say they're probably microbiologists. But I think at the moment, with the COVID pandemic striking us all down, our salvation lies very much in the hands of people like this team here, who are working with the virus team have been working on vaccines for us all. And without their work, which is an inquiry-based task, solving problems, finding out which vaccines will work, etc., doing tests, large-scale tests on large numbers of people, that's proper science in action for the benefit of humanity. And that is inquiry science happening before our very eyes. And the children in our classrooms will be doing no different. Scientists exist in communities, and I think that's one of the big messages here. Now, I've shown this slide before because it's a very important one to think about how we teach and learn science. If you are teaching in a more traditional setup on the left-hand side, where you have a teacher's desk and you have children in rows, you'll find it very difficult to engage children in group work as a community doing tasks together. Whereas if you manage to get permission to move the tables into something more on the right-hand side, you'll find that not only do you have a more fluid position moving around the classroom, but the children have a much wider area to work on, a bigger surface area, and they're facing each other, and dialogue is far easier in that situation. And you'll find that your children will progress much faster if they learn from each other in a team in that sense. So a simple thing about moving the architecture or changing the architecture of your classroom could easily lead to more fluent inquiry teaching and learning. So it's something to think about before we move on to the details. Now, it doesn't take much of a search on the internet or through books to find 101 examples of what is meant by science inquiry. I've chosen something from the English National Curriculum on the left, which gives you a set of 7 subsections which together make up what they called science inquiry, or in England it's known as working scientifically. And on the other side, I've found from other sources other people's interpretations of what might be part of inquiry. I'm going to lift one word out of the blue box to dwell on, and that is the word context. And if you're going to teach inquiry with children, I would try and urge you not to break down inquiry skills and teach a skill at a time with no context. Far, far better to look for context within the topic you're teaching. It may be plants and animals, it may be human anatomy, teeth and eyes and senses, it may be electricity or forces or motion or whatever. Whatever your topic is, try and look for inquiry opportunities within that topic. And it may well be that you can introduce measuring skills in the context of that topic, or asking questions for inquiries in the context of that topic. So try and look for a context for your inquiry teaching, and not just look at the skills themselves. And so there, in that way, you will find that there are opportunities for inquiry work right the way through your teaching. You don't have to wait for the inquiry week to start. And that's another important message. So look for contexts and be prepared to find inquiry at any time you're in your teaching. Now, on the left-hand side, we've got that working scientifically outline again, and I will call this the formal face of inquiry. But there is another face, less formal, and it's exhibited by the photograph I have here of shells. For younger children, inquiry can be quite informal, and it could involve just exploring and looking and wandering, moving to a park or the garden or around the school grounds or at home or even in the classroom, having a look at objects, shapes, smells, colours, collecting things, sorting things. They are, or even researching through books or the internet. They are all elements of inquiry, and we ought not to ignore them when we think of the broad range of activities which could be described as inquiry. So I want you to realise that it's not always necessary to think of fair test experiments when you're thinking of inquiry. The inquiry has different forms. Now, how can we make sense of formal, on the left-hand side, the formal science inquiry? Because it can look daunting with all of its subsections. And I'm going to offer you a way forward here, which is, for those of you who are new to inquiry, this I think will help you. I would like to offer you this three-phase, three-stage approach to thinking about inquiry. There's a part where you're planning what to do, a part where you're doing, and a part where you think about what you've done. So that plan, do, review is a model which I'm going to offer you, and we'll talk about each stage now separately as we go through the next few slides. Excuse me. So if you think about plan, do and review, each one of those sections can be divided into a number of skills to be learned. And in order to help children make progress in those areas, those skill areas, you will have to do what I've called some proper teaching. You will have to do some intervention type teaching where you are perhaps modeling an activity, modeling how to measure, modeling how to use an instrument, modeling how to think of collecting data and displaying data. So all of those sub-skills need proper teaching. They don't come natural to children, and you'll have to make sure that your lesson planning builds in, where appropriate, each of these small subsets of skills so that you can move children forward, give them practice, start with an example, and then allow them to carry on. And that involves teaching skills, which I've suggested here, math, modeling and scaffolding, and the idea of progression. We'll look at all of those in a moment. Simply, it's as I've said, moving from something very elementary and simple to a more complex and freed up approach to investigation. So doing things together, closely guided with the teacher and being a whole class task, and then eventually doing things on their own. So there is a progression, there is a gradual move from being guided to being freed. Here's an example of doing things together here in this photograph. You might want to think about what questions we're going to ask about our inquiry. What do we want to find out? But it may be something that we do together, and we listen to each other, and we listen to each other's ideas, and we build up a good inquiry question together as a group, as a social activity. So children are, if you like, they're all part of a modelled activity which is supported by the teacher. I mean, what's special about mammals is a question, for example, that might be found out by researching. It's not something you'd use experimental work with, but whereas which shoes grip the best could lead to a physical experiment. So asking questions is part of the planning process. Making a prediction or an educated guess. Now, that's part of the science inquiry process, and it takes some time to learn how to do this. And my best suggestion is to think about, I think that this will happen, but because this, that, and the other. You've got to justify your predictions. The best predictions always have a reason. I think the red car will win the race because it has the largest wheels. I think the green car will win the race. It has the smaller wheels, or whatever. So a prediction ought to have a reasoning element attached to it, so that you, in fact, could actually unpick the thinking behind the children's predictions. And finally, you'll need to plan what you do and how you do it and what equipment you'll need as a group. So planning has different phases. Now, what do we do? Well, of course, we've got to gather our equipment together, decide on the sequence of events, and as a team, decide who's going to do what, and then we get cracking and we start. And there'll be some measuring, there'll be some observing, and there'll be some recording of measurements, and that's all part of the doing phase. How do we do this? Well, maybe with a table of results, or maybe with a set of sketches as things change. Maybe the inquiry lasts over several days, and we're watching a seed gradually grow, and our observations are recorded in sketches. Or we may be doing something where we're using a ruler to measure things. We may even want to modify by changing one of the variables. Now, what happens if we add more weight, or if we double the weight, or if we wait for longer for the seed, or if the seed is growing in a dark room? So eventually we'll move towards changing variables. That's a high level skill and possibly not done till the upper years of primary school. It's all part of the doing process. And finally, let's think about what's happened with our measurements. Can we make sense of them? Was there a pattern? Have we learnt anything? What did we find out? We wanted to know this. That was our inquiry question. And we've discovered it. Or we discovered that. Oh, it didn't work. Or this is something we didn't expect. What have we found out? Because scientists always try to find things out. That's what inquiry is, finding out. So thinking about what we found out is very important. Looking for patterns in your measurements will lead you to a story about your inquiry. Within that story, you'll tell what you found out. In the two photographs here, we've got children telling their stories. One of them's being videoed on the right-hand side with a microphone. And this is a great chance for children to gain confidence speaking in front of others. The four children on the bottom left here, they're presenting their results. That's an inquiry team. And scientists will do this in real life at conferences across the globe. They might be webinar conferences, there may be real conferences. But being able to share your results with the science community is a critical part of the review process. And I would always urge you to allow children to do that. It's great fun. And they like speaking. And of course, some children will take to the fore as presenters, whereas perhaps they will be in the background when dealing with handling measuring instruments. You never know. You're playing to each one's strength, to allow children to enjoy their presentation moment on stage. We're going to have a look at measuring skills a little more closely now. On the right is a photograph of a young lad finding out how tall he is. And I think in most primary school classrooms that I've been in, there is some sort of measuring stick on the wall or set of numbers. And it's one of the early measurements all children like to do. And it's a way of recording a measurement. It's a proper inquiry skill. In this particular example, the lines represent whole centimeters. So this is one of the early examples of a child using a number and a unit to record their height. So that's a special skill, a measuring skill, and good teachers will enable those children to write down the number together with the unit, and they understand that a number with a unit is the way you take a measurement. On the left, of course, there's another message here, and it's about non-standard units. And we should encourage children early on to make measurements with non-standard units, like how many pencil widths is the table? How many steps does it take to cross the classroom? And what about the length of the classroom? Does it take more steps or less steps? We can have non-standard units when we start. And indeed, ancient civilizations used what we would call non-standard units here in the diagram such as this. And in fact, I know that people in the equestrian world still measure the height of horses using a hand. A horse might be 15 hands. We don't use cubits. We sometimes use paces, of course. We certainly have been using the idea of a foot as a unit of length in imperial measurement for many years. So non-standard units are good fun to try prior to using the formal rulers and scales that we would use later on. And that brings us to rulers and scales. Now, let's have a look at making measurements as one of our skills. Focus on the green pencil. How do we know how long the pencil is? Well, there's a skill or two to be learned here. The first, I think, is to make sure the end of the pencil is at the end of the ruler, which it just about is in my picture. And then, of course, we look along to see where the tip of the pencil reaches, and it reaches the end of 6 whole centimeters. And we can say the pencil is 6 whole centimeters long. And getting children to use a ruler, measure the length of the pencil like this, and then realize that you could write down the number 6 with a unit, 6 centimeters, and a sentence, the green pencil is 6 centimeters long, is where we're looking for our stopping point. We've measured the length of the pencil. And we know how to use this simple ruler. And there are ways to use it, and it's to do with getting the 0 mark at one end of the pencil and then looking at the other end. Well, of course, in the real world, pencils don't always behave like this, and they might be more like the yellow pencil. And the yellow pencil poses a problem because it's not 5 centimeters long and it's not 6 centimeters long. It's somewhere in between. And there aren't any numbers in between in this ruler. And this is the sort of ruler you find for younger children in many primary schools. It's a great ruler to use, but it can't tell you the length of the yellow pencil because there are no numbers between 5 and 6 on our ruler. I wonder, is there a number between 5 and 6? Okay, as teachers, you'll know what's coming next, of course. Yes, there are numbers between 5 and 6. There are many small ones, 10 in fact, and they're called millimeters. And hence, with an example like this on a display board, one introduces a progression from the earlier green and buff ruler with whole centimeters. We can use millimeters. And now the pencil has a length which maybe has more meaning to us. It is between 5 and 6 centimeters, but it's actually another 6 of the small millimeters. So one would say it's 5 centimeters and 6 millimeters long, or 56 millimeters. I don't think we would call this 5.6 centimeters when we're at primary school, because decimals will maybe take a little later in the mathematics curriculum to arrive. But where suitable, you will include that, of course, for your children. But 56 millimeters is fine. But you do need to recognize that there's some proper interventionist teaching needed in order to help children understand centimeters and millimeters. And of course, once you've introduced how to use a ruler, there's no substitute for plenty and plenty and plenty of practice. Get your children measuring everything in their room, everything in their bags. Measure the length of their fingers, measure the width of their ears, measure anything at all that you can find. So practice is going to help your children learn how to use measuring instruments. And I can't emphasize this enough. It's not good enough just to teach how to measure. You've got to be able to measure confidently on your own. And rulers are relatively cheap, and every child or every group can share a ruler and have a go at measuring things. Of course, there are scales on other measuring instruments, and you will broaden horizon of children, their horizons by including a number of different scales. And you ought to do this, of course, because rulers are not the only measuring instrument we'll be using. So simple weighing scales or digital timers or thermometers, they all have their own challenges, but they all have a scale and a set of numbers. So that's in common with the ruler. Some scales, of course, are color-coded, and it might be interesting to try and explain what do you think is happening in a color-coded scale later on in science life, dealing with acids and alkalis. There is a colored scale called the pH scale, which children in secondary education will come across. But you may even see these weather charts, or even confidence charts with the red face, the downy, unhappy red face, meaning I really don't understand this, and the green smiley face, meaning yes, I understand, and the yellow face in the middle, meaning, well, could you explain it again, please? I know some schools use a traffic light system, which is just another scale of understanding. Let's go back to the yellow pencil, which caused some trouble earlier on. If we're using this crude ruler with just whole centimeters, then we can't really tell you the length of the pencil. It could be 5 centimeters, it could be 6, it's somewhere in between. And we call that in-betweeniness an uncertainty. All measurements have some degree of uncertainty, and it depends on the measuring instrument. Sometimes it depends on the accuracy of eyesight of the observer, but there will be some uncertainty. And this is for you as teachers, really, just to recognize in your brain that, hey, we're only human and sometimes we have to use our judgment. So if it's longer than 5 but not as long as 6, well, maybe it's about 5.5 centimeters. We're not absolutely sure. We're uncertain. And that's fine to be uncertain. Science is full of uncertainties. So my message is, don't be worried about being uncertain, because you're allowed to say, well, we can't exactly pin down this measurement. It's between 5 and 6 or whatever. There could be big uncertainties with the ruler as the green one on the top here, where we're unsure by about 0.5 centimeter either way. Whereas if you're using a millimeter ruler, there's still uncertainties, but they're much, much smaller. Your degree of uncertainty is probably 0.5 millimeter either way. Now, later on in secondary education, children will be expected to understand the idea of uncertainties. But for primary children, I think it's important for teachers just to be aware that it's okay not to be perfectly accurate with a number measurement, because uncertainties are there in everything we do. So saying it's about this because this is as close as our measuring instrument can read is fine. Now, I've used progression several times and I will use it as we go through this presentation. The idea that you can start simply and then move to slightly more complex elements of inquiry is here under the title of progression. And these two rulers, I think, illustrate it perfectly well. I mean, the green and buff ruler is the one that you would use for younger children to give them the idea of numbers and a unit. You wouldn't give them the ruler on the left as their very first experience with a ruler. I certainly wouldn't, because it's too complex and it will cloud what you're trying to do. It's got too many numbers and too many lines. So think about the appropriate instrument for the level that your children are at. By all means, move to the rulers on the left later on, when children are a little older and more experienced of using rulers, but think about progression and be aware where the level of skill and experience that your children are at, so that you place appropriate instruments in front of them and don't expect them to do things to run before they can walk. Let's have a look at this little investigation that's been done by collecting empty cola cans. Sort of thing that you may have done with children, collecting objects during the week, particularly waste objects. So we've collected cola cans in our project, and on Monday we collected 2 cans. On Wednesday there were 5 cans, and we've made a list in a table of the days of the week and the number of cans. And here the teacher is showing how you can use drawings and blocks to represent the number of cans each day. So of course children will be able to do something like this after they've been shown by the teacher, but it's an example of how you would go from a real activity where you collect things to where you go to symbolizing what you've done by using symbols M, T, W, T, H and F. They are symbols representing a period of time called a day, and 2, 3, 5, etc. are symbols representing the real cans. So let's remember, or at least acknowledge, that that table of results is a table of symbolic representations of what happened in the real world. So even that stage has to be thought about carefully. The number 2 represents 2 cans, and it was what happened on Monday. Then the blocks are another way of symbolizing the number 2. So the number of blocks represents the number of cans. And you may even use a pictorial pictogram type scale where you draw cans instead of blocks. And that's where you might start with something like this. So dealing with 2 variables here, the day of the week plus the number of cans, but keeping in mind that keeping your chart simple, because you're introducing symbols, is a critical idea. Now, what we have here is another chart, And the chart is showing two different types of experiment. The one with the cans is on the top, and the one at the bottom is another experiment, which is about cooling water and measuring the temperature of cooling water. Now, at the top, I've described that as having discrete variables, and indeed they are discrete variables, because we've given whole numbers for the number of cans, and we've given whole units of time for the numbers of days. If we compare that with the continuous variables of the results below, you'll see that what you have there is any possible time from 0 to however long it took, and a child could decide on when they're going to make that temperature measurement. So there's a continuous range of times and a continuous range of temperatures available. Now that lower graph is much, much harder, and one wouldn't tackle that graph until you've looked at using discrete variables in an earlier stage with your learners. I apologise if you can hear background noise, but the council have decided to dig up the road outside of my bedroom window, so I'll try and speak over that. I mentioned scaffolding and modelling. They are techniques for teachers, and if you are here like this teacher and you're showing children how to place number 2 as a bar on a bar chart, you are doing a modelling task. You're saying, look, I'm going to do this for you to show you how to do it. And in so doing, you're giving children a helpful hand in enabling them to do the next one themselves. And that's a form of scaffolding as well. So you need to recognise that children need to practice things, but you need to show them first how to do it for themselves. So teacher modelling how things are done is a very important element of supporting learners. And then you allow learners to carry on the next steps on their own. Theoretically, this has been recognised by the Russian psychologist Lev Vygotsky, who talked about the zone of proximal development. And it's a suggestion that if we break tasks into smaller, manageable steps, then what is an enormous task looking far too big can be taken on board by making small steps. And just by expecting children to actually develop a small part of the longer journey, taking one step at a time. And he called this moving to your zone of proximal development, moving so that it does take some effort, but it's an effort to a place which you can achieve and gain a sense of achievement as well, achievable steps. So scaffolding and modelling will help children do this. And here's an example of how you might involve this in Enquiry, these techniques. Here's a sentence that needs completing, but rather than leave the children thinking of a word of their own, we can give them some words to choose from. We're scaffolding them. We're making the task a little bit more manageable. On the right-hand side, we're modelling. We could be talking to the children to say, look, we're going to make a chart, and this is what I'm going to do. I'm going to say, I need a horizontal line, and I'll draw that. I'm going to label all the days of the week along this line. So by articulating what you're doing for the first time with children, you are modelling your own thinking and your own actions, and they can then copy that. Eventually, they'll do it on their own, of course. We're going to have a look at some inquiry tasks now. And here's one I've used many times, and this is one set up at home on a little board. And there is, it's actually a well-eaten tennis ball that my dog would normally use. And it's a simple inquiry task. And of course, it's context. You'll have to think about which context would one use this task in. Well, I've got some questions for you. Clearly, you would not have a task like this if you were dealing with plants or animals. Of course, you'd have a task like this in the topic, perhaps, called movement or forces. Can you think of a question, a suitable question, that would match this equipment? We're almost looking backwards here from a finished experiment, trying to work out what was going on in the experimenter's mind. But the question may be, I wonder how far the ball will roll before it stops if we change the place that we release it from. And one could come up with a prediction, think about the measurements and how much you present your results. And you could do this as a task with children prior to starting. We could do it as a whole group. If you do an experiment like this, you're bound to end up with a set of results in a table. And I've got one of my results here, 25 centimeters. I released the ball and it went 71 centimeters along the carpet. And I've noted there that there is a discrete variable there in the start height, because I've already labeled those particular heights. You just have to choose one of them. But it could be that the ball goes any sort of distance, and that's a continuous variable. So you're introducing just one slightly harder continuous variable for the children to measure. And what occurs to me when I look at something like this slide is that we've gone from one form of symbolizing, which is the numbers, because the numbers represent real positions and real distances on the carpet, and they're represented in symbols we call numbers. But even the pair of numbers is represented by a dot on a space, and that really is symbolic. It looks nothing like the ball and the slope and the carpet. So let's recognize how abstract this science can become in front of children, going from the concrete through the symbols to the abstract point. And it's not something that children will automatically be able to understand. You need to be sensitive to that transition from concrete to abstract. Okay, what about younger children? Can they do inquiry? Of course they can. I've suggested informal inquiry is something that is suitable for many young children. Can they have the joy of just finding out? Do they have to do loads and loads of measurements? Or can they be inquirers in their own right? And I think they can. And one of the contexts I've used have been nursery rhymes. Here's an example of a child's nursery rhyme, well known. Well, can we find a context for some exploration and inquiry here? Well, I think we can. And I think it might look like this. Very simple, to get a bit of a shelf, piece of wood and support it with maybe a textbook. And then a number of objects, and we can see what happens. We're just going to see what happens. Does it roll? Does it slide? What shape is it? And the language is emerging: roll, slide, flat, round. So dealing with language, with simple tasks, with observing, it's a very simple piece of science, and it comes from the context of the nursery rhyme. And what about those drinking cups? Will they reach from the top to the bottom when they roll? No, they won't. But you and I could probably tell why. Let's see if the children can work out why. Here we have more children here, and they're also doing inquiry activities. They've been out collecting things in the woodland. They've decided to gather things together because they belong in one of the hoops, one of two groups. They are sorting. They're classifying. They're observing and describing. All very good skills for young learners. And they're doing it together on a big table where they're sitting around. And that's really good inquiry science. It doesn't look like science, but it is. And you can use any type of everyday object for this sort of thing. Here are a number of things that you might collect and have children do the same sort of activity, sequencing, grouping, and guessing what they're thinking of. I'm going to have a secret choice here. I'm going to use some words from our word list. And you've got to see if you can see the object I'm thinking of. I might say it's a dull color. It's spiral. It has no jagged edges. It's one color all the way through. Yes, I think it's this. You're correct. It's this one here. Now it's your turn. So by just describing objects and having a simple Can you guess my object game? Or you could draw the objects. Can you see which object I've drawn? They are all observing and describing skills. And you can do it with a number of different objects. We've talked about collecting cola cans, and there are lots of worksheets available on the market where you can do this sort of thing, collecting and grouping things together. Here's one I quite like, where children have brought in their cups, their drinking cups, and we gather them together as a sort of activity during the week. Can we gather all our cups together from home, different coloured ones? And then we'll do a sorting activity. And we can group the ones which have got handles. And we'll have the blue cups in another group. But there's another group in the middle, which are the blue ones with the handles. So just an example of how you might use some mathematics, some easy descriptions with an inquiry task. And don't forget, there are plenty of examples in the home where we arrange and sort objects. Well, I hope that you do in your homes. It's very easy for homes to be rather messy, but we do our best to keep our life tidy. And there's an example of sorting objects by shape and by function. Okay, as teachers, what can we do for help? Are there places we can turn for help in this sort of inquiry science world? Well, you could have a good set of textbooks which are based on inquiry, which the Max Science books do have, and just giving you an example of in every unit that we have, there are many little minor inquiry tasks which are in the yellow boxes, and your children can work through those, and they're all inquiry within a context of that particular unit. So you'll find good inquiry activities available in textbooks, rather like Max Science. Or if you want the electronic version of Max Science, the teacher presentation kit, it also includes activities for inquiry, and lots of examples for you. Here's something from the teacher presentation kit. It's about asking the right question, or an appropriate question for this particular investigation. Can we come up with a decent, good, pertinent inquiry question that these children will be finding out? Well, yes, here are some that we might have, but some are appropriate and some, I'm afraid, are not appropriate. And that's a task you could create for children to make a decision on. Are boys' shoes more smelly than girls' shoes? Well, you probably, as teachers, will know the answer to that, but it's not an appropriate question for this experiment. I've chosen this from the teacher presentation kit as well, and added 2 speech bubbles, because I think that's a way of engaging children in a task by having a couple of children model the questioning, and then over to you, children, what do you think? And you can do that with the activities in Max Science. If you're really stuck for ideas for more inquiry, then there's a whole set of inquiry boxes available from Macmillan, and each one is a sheet full of inquiry ideas for science. And there's some for every level, and they do follow the Cambridge Assessment International Education program, so that they are compatible with many syllabuses as well. But they're all full of ideas, so you don't have to always think of the inquiry tasks yourself. And I'm going to finish off with a little bit of language that I think is very useful when you're dealing with inquiry for older children. And the idea that when you're doing an inquiry activity, you think about, if we change this, what happens to that? That's a really powerful structure that I think it's useful to have even displayed on a display board for inquiry. If we change, for example, in this case, the weight we add, what happens to the length of the elastic band or the length of the string? If we change the temperature of the water, what happens to the time things take to dissolve? So here's a useful structure. If we change this, what happens to that? And you may know, recognize as teachers, that what we're dealing with are 2 variables. We're changing one variable, and we're looking at what happens to another variable. One is being controlled by us, and the other one depends on the choice that we make for the first one. One is independent, the one we control, and then what happens does depend on what we're controlling. Two variables, if we change one, what happens to the other? But that sounds quite sophisticated, but I would expect children age 11, 10 or 11, certainly 12-year-olds, they should be able to cope with, if we change this, then what happens to that? One of my favourite home experiments that I've been sharing with people during lockdown has been the fridge magnet and paperclip experiment. How many paperclips can your fridge magnet lift up? What about if you place a piece of paper underneath the magnet? What about two pieces of paper? If we change the number of paper sheets, what happens to? So we've got one variable, changing the number of paper sheets, and the second variable, which depends on what happens first with the sheets, the second variable is the number of paper clips. And is there a pattern? Can you find something out? Is there a discovery here? Well, in fact, you won't be surprised to know that there probably is a pattern, and it could involve drawing a chart. And I'm not going to dwell on this because it's easy for you to do at home or with your own families, or indeed in a classroom. Just get yourself the biggest box of paper clips you can. And you'll find that young children, even with the help of mummy, in this case, during lockdown, my good friend Ruben has done this very same experiment, and he's got his results, which he photographed with the help of his mum, and he's done the paperclip experiment. And he's very proudly wearing his goggles, science goggles there, although he didn't need to for this experiment, but he likes to wear them anyway when he knows he's doing science. And so that brings us to the end of the presentation, really. I want to go back over some of the important messages en route. We've talked about working collaboratively in groups. I've mentioned my simplified approach to planning, doing and reviewing, 3 stages in inquiry. Don't forget, for younger children, younger learners, the informal nature of inquiry. Yes, we talked about progression in skills, having appropriate equipment for the level of your children, and the role of the teacher in providing scaffolding and modelling activities is an interventionist teaching, is proper teaching, particularly with early skills, and the support that there is available to you. So that brings me to the end of this presentation. I hope I've not rushed through too much. There's plenty for you to absorb, but of course there's plenty of inquiry science out there for you to do with your classes. I wish you good luck with your inquiry science, and I hope that I hope to hear from some of you how things have happened and how things have worked and how your children have coped. I'll try and do some of these experiments you've seen in the presentation. They're really good fun. Thank you very much.
Thanks so much, Bob. That was great.
I think now there's going to be a time when we could have some questions. We've got about 10 minutes, I think, Elliot.
Yeah, I've been having a look at questions as they've come in. So we've had one which was, are there any rules to keep in mind while framing the main inquiry-based question to take the learning forward?
Are there any rules? Well, I think one of the first things you're going to have to do as a teacher is to make sure that the inquiry question you've chosen or your children have chosen is achievable. So you may have to do some sifting yourself through a number of suggestions, and you might have to gradually, lightly steer your children to a question that you know is achievable. But that process is not a bad thing to go through in itself, because children might ask all sorts of questions which you just don't have the equipment to do. So in your own mind, you probably have an idea of the sort of inquiry question which is appropriate for the topic and the equipment that you have. And so keep that in mind. You may well have to steer your children's inquiry question to one that's achievable. That's the important thing.
Great, thanks, Bob. We also had a question about what the age of students you teach was, or perhaps, I suppose in this context, what the age of students you were thinking the task you were showing
Okay.
in the
Okay.
presentation were for?
Okay. Well, there's several answers to that. With younger children, I've done inquiry with children age 7 and 8 year olds who have done inquiry with, for example, um, shadows and hand torches in the dark, and looking at the length of shadows and how they relate to where the torch is, that sort of thing. An open-ended inquiry. With younger children, I've done inquiries where we've looked at collecting leaves or collecting sticks and stones and describing and making patterns with them and ordering and sequencing them, large to small. With younger children, you could easily do that sort of thing, particularly outdoors. You can do recognizing. If you give children, for example, if you give children a set of pictures of tree leaves, and we go for a walk and we try and match the tree leaves to those names of trees in our picture, that's an inquiry task as well. Whereas someone like Ruben in the last slides, he could not have done that task himself without the help of his mummy. However, he did achieve it with the help of his mummy. So there's a message there, I think, to say, look, even quite complex, apparently complex inquiries, which involve measuring, counting and recording and making a bar chart, which you might normally say is the realm of someone who's from age 9 to 12, could be done by a younger child with support.
Absolutely, that's great, Bob. We had a question which was, could we involve students in framing the inquiry questions as well?
Yes, absolutely. And it goes back to the first idea of allowing them with some sort of structure, and you might like to offer them 2 or 3 inquiry examples of questions and ask them to rate each one and choose the most appropriate one. And you could deliberately do that by having a couple of totally inappropriate questions which can't be answered at all by school children, and one that can. And so the idea is they select the most appropriate question. So you might like to scaffold their involvement with questions in that way to start off with. But eventually, why not get children to group together and say, look, your task is to talk to each other and decide amongst yourselves the best inquiry question for this piece of work we're doing now. And you'll find that you'll find 2 or 3 really good questions coming out of groups. They can discuss which they think is the most appropriate. And it may be that different groups tackle slightly different inquiry questions. Provided they've got the apparatus to do the work, then why not let them solve their own inquiry questions?
That's great. I think that might have partially answered the next question I was looking at, but I'll just pose it in case you've got anything to add. So, are there effective ways to set the context for the students to then arrive at the inquiry-based question? Or
Well, I think it's all part of your lesson planning as a teacher. Not every lesson has to be full of inquiry for a start. And you might say to yourself, well, with my class, we've not actually done much inquiry work, any sorting, grouping, measuring for the last week or so. It's about time we looked for an opportunity. So you could genuinely try and find an opportunity in the work because you know that it's time that you've got to try and push forward ideas of measuring or using rulers or whatever, or graph work. So you engineer an inquiry because you know it's going to lead to you showing children how to make a bar chart. And that's the reason why you're doing this inquiry, because it focuses on how to make a bar chart. And so part of your lesson planning will be, what skills have we progressed in? What skills are we light in, we've not had experience with? Making a bar chart is one. It's the next one on the line, really. Let's try and look for an inquiry which uses a bar chart. And so you build into your lesson planning an appropriate activity to solve or to target the skill area that you want. But of course, it's not just that skill area. You do the whole activity, but you focus on the skill area of bar charts, for example. So you choose depending on what your objectives are as a teacher for those skill areas.
Brilliant. Thanks, Bob. Someone's asked, I'm not sure if this is something you've got experience of, but do you have any tips for doing inquiry-based learning online for teachers who are maybe not in school at the moment?
Okay. Well, I have had some experience because I did some webinars for local people here in Scotland, for particularly aimed at parents who were in lockdown doing home tuition. And of course, what you have to do is have a look at the resources in your home. And your home is full of resources. Sometimes you don't recognize them, but the kitchen is where to start, because the kitchen has measuring jugs, measuring instruments, has beakers, has drawers of things which are different shapes and sizes, things that have got handles which are made of wood, but something else is made of metal. So materials abound. Things that can contain water. You have a sink in the kitchen. So, for example, there's a host of activities in the kitchen environment. Health and safety warning. There's a lot of danger in the kitchen environment too. So keep sharp knives and naked gas flames, for example, and electrical points, keep them separate from children, or at least intervene yourself to do the difficult parts, which might have some hazardous element. But kitchens, I would say, and if you have a garden, of course, gardens are great as well. But if you're not lucky enough to have a garden, then look for opportunities. For example, in my room here, I'm looking, you can't see me, I've got a series of photographs on the wall in frames, and they're all different shapes. And I could measure them, I could describe the shapes, I could do one of those, I'm thinking of a picture shape, I'm going to describe it, what's on the picture, you've got to decide which picture I'm thinking of, that sort of thing. And then you take it in turns. So your home's a rich environment full of probably even more things to find out about than even a classroom environment. So yeah, so use the things you find around the house.
Thank you so much, Bob. I know a lot of teachers have been stuck at home at the moment, so that must be really useful for them to hear. I think that might be all the questions we've had, which is lucky because we're getting to the end of our hour here. So all that's left to say really is thank you so much to everyone who's come along today, and everyone who's asked questions or put a comment in the box. And thank you, Bob, for taking this session. It's been brilliant. I've really enjoyed it, and I'm sure everyone else has as well. If anyone would like any more information, then you can see our website on the page, as well as all our social media channels, and you can just reach out to us by messaging on any of those or sending an email. You'll be getting your certificates in an email soon, and as well as a copy of the presentation and a recording that will go up on YouTube later. So thanks everyone so much for coming. And
can I say something, Elliot, before we leave? Here's a final message from me. One of the things I discover from teachers is that they are reluctant to do inquiry work with children because they don't know the answers. And teachers feel uncertain because they don't know what the answers should be. And I say to you, that's fabulous not to know the answer, because it means it becomes your inquiry as well. And it's almost better not to know the answer, because the children will tell you the answer. Whatever they discover, then that's the answer. So don't ever feel hesitant. Just go forward and enjoy that process with youngsters.
Thank you so much, Bob. It's been great to have you here with us today.
Well, good luck, everyone, and hope we meet again sometime, either virtual or in real life.
Okay. Bye, everyone.
Bye-bye.
Thanks.